Hi everyone, for today's lesson, we are going to learn how to solve systems of equations graphically. Our learning targets for today are for you to be able to say, simply, I can solve a system of equations graphically, which means that we're going to be graphing multiple equations at the same exact time and looking for points of intersection. Before we get started with today's lesson, you need the following materials. First of all, you're going to need a graphing calculator. If you don't have a graphing calculator, it's not a big deal. You will use that graphing calculator next time that I see you in class. You're going to need something to write with, and you're going to need a straight edge of some kind. So if you need to pause the video to make sure that you have these supplies, then that would be super helpful. When it comes to a straight edge, all you really need is the side of a calculator, a side of a book, piece of paper. Anything can really serve as a straight edge. So recall back from Algebra 1 what a system of equations was. So we used to graph systems of equations where we had multiple lines and we would look for points of intersection. And a system of equation consists of two or more equations, and the solution of the system is where the graphs would intersect. So we would look for different kinds of intersections. So sometimes you would have two lines that would go in independent directions, and then they would intersect at one specific point. So when graphed, the lines intersect at just one point. And one thing that you can always tell whether or not these equations would just intersect is that the slopes would be different. So an example of something that you might see would be like y is equal to 3x minus 1 and y is equal to negative 2x plus 4. Both of these are linear functions. They both have slopes that are different. They're both going in their own path, and they will intersect at some point. So that is considered one solution. No solution is when graphed the lines do not intersect. And if the lines do not intersect, what you're going to see in the equation is that the slopes are the same, but the y-intercepts are different. So when you get your equations in y equals mx plus b form, slope-intercept form, what you'll notice is that you'll have something like y equals 2x and y equals 2x minus 7. Both of these equations, these lines, have the same slope, but the y-intercepts are different. Like for our first equation, the y-intercept is 0, and down here the y-intercept is at negative 7. So therefore, these two lines will travel in different directions and never intersect. These are called parallel lines. The next type that you will see is infinitely many solutions, and when graphed, the lines coincide, because they are essentially the same exact line. The slopes are going to be the same, and the y-intercepts are the same. So why would you ever talk about that? So it's kind of like this. A lot of times the equations are in disguise. So for example, if you have something like y is equal to x plus 1 and something like negative 2x plus 2y is equal to 2. If we were to solve for y, what we would notice is that we would add 2x to both sides. We would end up with 2y is equal to 2x plus 2, and then we would divide every single term by 2 to end up with y is equal to x plus 1. When simplified, or when you rewrite that equation, you find that it's the same exact equation as the other, just you couldn't tell because of the type of structure that it's in. So this is known as infinitely many solutions, and the only thing that you're going to see here is one line. So those are the different types of solutions. And hopefully what I just talked to you guys about is nothing new. You remember it from when you were in Algebra 1. So now what we're going to do is we're going to practice graphing this system of linear equations, making sure that at the very end, we check our solution algebraically. So looking at letter A, what we do when it comes to graphing these types of equations is we graph them independently. So looking at my very first equation, I have y is equal to negative 3x minus 2. So my y-intercept is at negative 2, 0, negative 2. So I'm going to go ahead and start by plotting that point. That's my starting point for applying the slope. My slope is negative 3, and the way that you plot that is you go down 3 to the right 1. Now, because we're graphing a system of equations, you don't want to stop at 2 points. Instead, you want to plot every single point possible on that line using the slope. So it doesn't make sense for me to go down 3 to the right 1 anymore because I'm off the grid. So instead, I'm going to use the slope backwards, which means I'm going to rise 3, 1, 2, 3, and run backwards 1. So it's kind of like the opposite of the slope. Instead of going down and to the right, I'm going up and to the left. 1, 2, 3, and here's my point. And the reason why we want to come up with as many points as possible is because of the fact that one of those points might end up being our solution to the system. So there's my first equation. Cool. So now I have my second equation. And looking at my second equation, I have 5x plus 2y equals negative 2. And I would recommend just transitioning that equation to slope-intercept form, which essentially means solve for y or get y alone. So the way that you do that is we're going to start off by subtracting 5x on both sides. Then we end up with 2y is equal to negative 5x minus 2. So now what we want to do is we need to get y alone, and I'm going to divide every single individual term by 2. And what that's going to do is eliminate the 2's next to the y to get y finally alone. And I'm going to simplify each individual fraction. This is going to turn into negative 5 halves x minus 1. So now my y-intercept is located at negative 1, so I'm going to plot that first. And then from here, I'm going to apply the slope, which is go down 5 to the right 2. So I'm going to count 1, 2, 3, 4, 5, and then to the right 2. 1, 2. And just like before, we want to come up with every point possible on this line. So I'm going to go up instead of going down. I've ran out of grid space. I'm going to go up 5, 1, 2, 3, 4, 5, and I'm going to run backwards 2, 1, 2. And I land at this spot, which isn't that nice that we plotted every single point possible on the other line. So now I'm going to draw to the very best of my ability a straight line that's going through all of these points. So now I can clearly see that we have ourselves a point of intersection. And that point of intersection is located starting at 0, 0, negative 2, up 1, 2, 3, 4, negative 2, 4. So now what I'm going to do is I'm going to verify that that is indeed the answer by plugging this value directly into my both equations. So you have to check using both. So I'm going to check negative 2, 4. So that means that I'm going to let x equal negative 2, and I'm going to let y equal 4 into both equations. So starting with my first one, I just want to show that it is indeed true. So I'm going to write 4 is equal to negative 3 times negative 2 minus 2. So this is going to be 4 equals, this is 6 minus 2, and that is true. 4 does equal 6 minus 2. Cool. And now whenever you check, we always check back into the original problem. So instead of me working with negative 5 halves x minus 1, I'm going back to the original. So I'm going to write 5 times negative 2 plus 2 times 4. And I'm going to show that that equals negative 2. So this is negative 10 plus 8 equals negative 2. And that is true. Negative 10 plus 8 does indeed equal negative 2. And because I showed that negative 2, 4 works for both equations, we must conclude that negative 2, 4 is indeed the solution to our system. So I hope that what I just showed you guys is nothing that you have not seen before, something that you feel pretty confident about. When I see you next time in class, we will work on the solo question. All right, so now how does this have anything to do with quadratics? I mean, this is day 20 of unit 1. How does this have anything to do with quadratics? Well, this is how. So these are systems of equations, and as you guys know, systems, like equations, can be linear, but they can also be quadratic, absolute value, circles. We have lots of different equations out there. So using your head, how many solutions do you think are possible for a system consisting of one line and one parabola? So if you think about this, how many are there? Well, one line and one parabola. You could have a parabola in which the line does not intersect with the parabola. This would be considered no solution. You could have a parabola in which there's a line and it only intersects at one point. It could be a horizontal line or a vertical line, but it's possible to only end up with one solution. And then finally, you could have a parabola with a line intersecting at 2 points. So 2 solutions. So up to 2 solutions. Please go ahead and try the one line and one circle on your own. This will be something that we discuss when we come back, when I see you next time. All right, so let's go ahead and move on to the next one. So now you guys can see that we can work with circles, we can work with parabolas. So looking at example number 2, we're going to solve a quadratic linear system. And even for this first one, this is a quadratic relation. This is a circle because it has both an x squared and a y squared. So that tells you that we're going to be working with a circle for this example. So the problem with this equation is that x squared and y squared are not alone. So we're going to start off by adding 25 on both sides. And when you do that, you end up with the equation of x squared plus y squared equals 25. So from that equation, I know it's a circle because x squared and y squared are both squared. I know that because I don't have like a plus h, or I'm sorry, a plus or a minus inside of parentheses, this tells me that my center is located at 0, 0, and my radius is always this number. You're taking the square root of it because this is equal to r squared. So my radius in this case is 5. So let's go ahead and plot 0, 0. And then I always count north, south, east, and west. North 5, south 5, east 5, west 5. So here we go. Counting up 5. 1, 2, 3, 4, 5. There's north. 1, 2, 3, 4, 5. There's south, east. 1, 2, 3, 4, 5. And west. 1, 2, 3, 4, 5. To the very best of your ability, please go ahead and try to draw in a circle. To the very best of your ability. All right, so next we're going to draw this line, and we have y is equal to negative 3x plus 5. So this plus 5 is our y-intercept. So I'm going to go up to 5. 1, 2, 3, 4, 5. And then I'm going to apply the slope by going down 3 to the right 1. So I'm going to go down 3, 1, 2, 3 to the right 1. Down 3, 1, 2, 3 to the right 1. Down 3, 1, 2, 3 to the right 1. 1, 2, 3 to the right 1. 1, 2, 3 to the right 1. And I'm going to continue going up as well. 1, 2, 3 to the left one, and those are all of my points that I can plot. Using your straight edge, go ahead and draw a line going through all of these points. And I know this one might be a little bit challenging depending on how well you drew your circle, but in this problem, there are 2 points of intersection. One that's our north point, that's a little bit easier to identify, and then this one down here where I was adjusting my circle. So this point up here is located at 1, 2, 3, 4, 5. So this is 0, 5. And down here, this point is located at 1, 2, 3, negative 1, 2, 3, 4. So that is at negative 3, oh, sorry, excuse me, positive 3, negative 4. That's a positive 3 right there. All right, so this problem has 2 points of intersection. And so we will have 2 points that we will need to check. So let's go ahead and start by checking the ordered pair 0, 5. And we're going to plug 0, 5 into both equations. So that means I'm going to let x equal 0, let y equal 5. And so that is 0 squared plus 5 squared minus 25. Does that equal 0? So 0 squared is 0. 5 squared is 25. Is 25 minus 25 equal to 0? Why, yes, it is. So now I'm going to check 0, 5 in the other equation. So I'm going to write 5 equals negative 3 times 0 plus 5. Negative 3 times 0 is 0, and 0 plus 5 is 5. So yes, I've shown that 0, 5 does indeed work for both equations. So now I need to check the other one. So I'm going to check 3, negative 4. So I'm going to plug 3, negative 4 into my original problem. So that is 3 squared plus negative 4 squared minus 25. Does that equal 0? So please make sure that you are careful with using parentheses, because if you're really dependent on your calculator and you don't use parentheses, your calculator will not produce a correct answer for that particular problem. So 3 squared is 9. Negative 4 squared is a positive 16. Minus 25, does that equal 0? So 9 plus 16, that's 25. And 25 minus 25 does indeed equal 0. So cool, I've already checked my first equation. And now I'm on to my second equation. So I need to show that negative 4 is equal to negative 3 times 3 plus 5. Is negative 4 equal to negative 9 plus 5? It is. So I have shown that both 3, negative 4 and 0, 5 are indeed solutions. So when you guys are doing your assignment, the expectation is that you are going to be checking your solutions in both of the equations that are given to you. Let's go ahead and look at letter B. In letter B, this time around, I have y equals x plus 2 squared minus 3 and y minus x equals negative 1. So my first equation is a vertex, is in vertex form. It's a parabola in vertex form. So what we can do really quickly is we can create a table of values. And what's really nice is that we know what our vertex is. Our vertex is the opposite of what we see, and then exactly what we see. So that is negative 2, negative 3, and I'm going to put it into the center of my table. And then I'm going to select values on both sides of my equation, of my x values. So I'm going to let x equal negative 1. I'm going to let x equal 0. I'm going to let x equal negative 3, and I'm going to let x equal negative 4. So I'm going to plug these values in, and I'm going to write y is equal to, and I'm going to pick the easier numbers. So I'm going to let x equal negative 1, and then I'm going to let x equal 0. So that is going to be negative 1 plus 2 squared minus 3. So negative 1 plus 2 is 1. 1 squared is 1. 1 minus 3 is negative 2. So I'm going to let x equal negative 1, and our output was a negative 2. So I'm going to put that in, and because of symmetry in my table, I know that I will plot negative 3, negative 2. So now I'm going to let let x equal 0. So I'm going to write 0 plus 2 squared minus 3. So 0 plus 2 is 2. 2 squared is 4, and 4 minus 3 is 1. So using symmetry, I know that my other point is going to be at negative 4, 1. So now I'm going to plot all 5 of these points. So here is negative 4, 1, negative 3, negative 2, negative 2, negative 3, negative 1, negative 2, and 0, 1. And to the very best of my ability, I'm going to connect all of these points with my parabola. So now my next equation, I prefer to turn this into y equals mx plus b. So I am going to add x to both sides so that I end up isolating my y, and I end up with y equals x minus 1. My y-intercept is located at negative 1, and then my slope is positive 1. So I'm going to write 1 over 1, 1 over 1, 1 over 1, and that's kind of going away from my parabola. So I'm actually going to go the other way. So I'm going to go down 1 to the right 1, down 1 to the right 1, down 1 to the right 1. And using my straight edge, I'm going to draw a straight line going through all of these points. And there appears to be 2 points of intersection this time, 2 locations. And those locations, if we look at it really, really closely, appears to be at the vertex, which is at negative 2, negative 3, as well as this point right here, and that point is located at negative 1, negative 2. So now we have 2 different points that we need to check. So let's go ahead and start off by checking negative 1, negative 2. So I'm going to write y is equal to, so y is negative 2, so negative 2 equals, we have negative 1 plus 2 squared minus 3, so that is negative 2 equals, this is 1 squared, which is 1, and 1 minus 3 doesn't equal negative 2. So now I need to plug it into the other one, so that is y, which is negative 2, minus negative 1, which is x, and show that equals negative 1. Negative, negative makes a positive, and negative 2 plus 1 is negative 1. So that is a true statement. So now I need to check negative 2, negative 3. And I'm going to plug negative 2 into my original function. So I have negative 3 equals negative 2 plus 2 squared minus 3. So negative 2 plus 2 is 0. 0 squared is 0. So negative 3 does indeed equal 0 minus 3. That is true. And finally, we have negative 3 minus negative 2, because I'm plugging it into my other equation up here, y minus x. So negative 3 minus negative 2 is equal to negative 1. Negative, negative makes a positive, and negative 3 plus 2 equals negative 1. Because I have double check marks, that means that we are all good. So now we have one more problem, and that is a solo question, and I would like you guys to go ahead and try that when I see you next time in class. So finally, for example, number 3, what we want to do is we want to use a graphing calculator to check our answer from 2b. So looking at 2b, our solutions were at negative 1, negative 2, and negative 2, negative 3. And here's how you check using a calculator. Looking at our 2 equations, we're going to use our equations in their y equals format. So what we're going to do in our calculator is we're going to let y sub 1 equal x plus 2 squared minus 3. And we're going to let y sub 2 equal x minus 1. And so whenever you input into a graphing calculator, you need your equations to be in a y equals format. So in my graphing calculator, I'm going to press y equals, and I'm going to clear out any equations that I already have in there. And I'm going to insert my y sub 1 being parentheses, x plus 2 squared minus 3. And for y sub 2, I'm going to insert in x minus 1. From here, I'm going to press zoom 6, and that's because zoom 6 will give you a standard 10 by 10 grid. So I'm going to press zoom 6, and I'll write that down for those of you who need to see steps. So I pressed zoom 6, and what I see here is the exact same parabola that I graphed with 2 points of intersection or some kind of intersection taking place. So what I can do is I can press second graph, and that's going to show me my table. So I'll write down that step as well. So I want to look at the table. And that is with second graph. I'll write that down right here. And now I'll zoom into my graphing calculator so you can see what I see. And in my graphing calculator, you can see that at -2, where x is -2, both y sub 1 and y sub 2 are located at -3. And at x equals -1, both y sub 1 and y sub 2 are at -2. At every other point, their y values are different, like 6 and -6, 1 and -5, -2, -4. But just right here, they are the same, indicating that those are solutions to the system. There are 2 more problems, and they are both solo questions, and we will do those problems next time I see you in class. So that concludes today's lesson. If you have any questions over anything that I talked about, please feel free to email me. Otherwise, I hope you have an amazing day.